So this is a presentation on how you can infer from a sample to a population. Remember, if you get data from a population where you have the data on every single observation, then you know what the population looks like. You don't have to do any asking yourself, is this significant or not? But if you are only drawing on a sample from the population, a random sample from the population, you have to do some thinking before you can say that what you see in the sample is likely also something you would see in the population. So I want to take us back to something we talked briefly about at the beginning of the term, and that's this idea of the mean and the standard deviation and what that actually tells us about the distribution of values of a variable. So the mean, I just drew out what is basically a normal distribution for you. You can see this curve. It looks like a bell-shaped curve. A normal distribution has values that are distributed roughly equally around the mean, so about the same number of values above the mean as below the mean. And also the values steadily taper off at the ends. And so you get fewer and fewer cases at these higher values and at these lower values. And what we know about a normal distribution is that about 68% of values will fall within one standard deviation. And 95% of values in your distribution will fall within 2 standard deviations. And it is very unlikely to fall at this end here, which is below 2 standard deviations, or at this end over here, which is above 2 standard deviations. If you get a value that's below or above this, it's very unlikely to occur, and that becomes useful to us later. So I wanted to show you a distribution, an illustration of one of these distributions, and I actually went back to the hours worked, and I wanted to figure this out for myself. So this is a chart of hours worked. I excluded all of the 0 hours, people who worked 0 hours, because that would not be a normal distribution. We would have a big set of cases right here on the end, and you would no longer have a normal distribution. But if you exclude those folks, you actually have something of a normal distribution here. You can see where the mean is. The mean is at about 41. You can see where one standard deviation below and 1 standard deviation above, and 2 standard deviations below and 2 standard deviations above. And I went and I looked at the data and I figured out what percent of cases were here, more than 2 standard deviations away from the mean. And it turned out that that was all cases with 12 hours or fewer working, and that was 3% of the values in the entire sample. And if I were looking for what percent of cases are 1 standard deviation or lower, it turned out that that was 14% of the values, and that's 14% lower than this 26.8 hours worked. If you look at the other end, you can see the same thing. 2 standard deviations above would be working 70 hours a week or more, and there were about 2% of our values there. And 1 standard deviation above is working about 56 hours a week, and there were 14% of our values are 56 hours a week or higher. And I'm going to go back to the little chart here. And in fact, the distribution of those values for hours worked aligns pretty well with what we would see with a normal distribution. So that when I talk about a normal distribution, that's what I'm talking about. And the important observation is that values more than 2 standard deviations away are very unlikely to occur. So I want to talk a little bit about different types of means that you can compute. You can compute, if you can find all of your observations, if you can find every unit in the population, you can compute the mean and the standard deviation of a population. That would be what is true about that population. And you'd know, it was what you would know if you could capture every case in that population. We call that a parameter, a population parameter. And we are very seldom able to actually capture, it's not like financially feasible to capture every observation in the population, but we always know that the population's out there, and we know that the population has a true mean and has a true standard deviation. These are the Greek symbols for those things. More likely, you're going to draw a random sample from the population, and from that you will compute your mean and your standard deviation. These are estimates. They are estimates based on the sample that you drew. What we have to do is figure out how good an estimate that is. How confident can we be that the estimate itself represents something happening in the population? And what we do to the leap we take to get to that question is that we think about what would happen if we drew means from many different random samples of a population. So far in your GSS data, you have one random sample of that population. But what would happen if you drew many independent random samples from that population? Each of those samples would look a little bit different. Each would have a different mean, and those means would themselves have a distribution. And that distribution is going to help us with our decision making about whether we can infer from a sample to a population. So I am going to talk to you about the central limit theorem. You do not have to memorize the central limit theorem. I just want you to kind of see what its power is, and I'm going to show you some illustrations of it. The central limit theorem basically says that over many samples drawn from any distribution, the distribution of sample means will take the form of a normal distribution. So for anything in the population, any variable in the population, no matter what its distribution is in the population, if you draw many random samples of it, the mean of the population, those random means will form a normal curve. Really, it's so cool. And the larger your sample is, the more condensed your normal curve will be, the more confidence it's going to give you. That's why we like larger samples. They have less noise. But I want to show you, this is a website you have a link to in your Moodle page. This is a really cool illustration of this. This is at Brown University, and they have these animations of probability distributions. And I'm actually going to skip down to the central limit theory. And I just want to show you what I mean by many random samples from the same population creating means that have a normal distribution. So this up here is a distribution of values. There are the same number of cases. Each value has the same number of cases. So we call that a uniform distribution. Think about if in the United States, each age had exactly the same number of people. Each age group had exactly the same number of people. So that there were 1 million 1-year-olds, 1 million 2-year-olds, 1 million 3-year-olds, 4-year-olds, 5-year-olds, etc. That's what a uniform distribution would look like, that each value had the same number of observations. So if I have a sample size of, let's take a sample size of 5. So I'm going to draw 5 numbers, 5 observations randomly from this distribution up here. And I'm going to compute the mean, and I'm going to look at how those means get distributed. So if I just do one mean, that's where it ended up. So for the observation, for the 5 observations that we drew, the mean was here. If I draw 37 samples, you can start to see that it's starting to look a little bit like a normal curve. I'm going to draw another 50. I just moved my little bar over here. Again, each of these dots that is falling represents a random sample from that distribution in yellow above. So we're going to do 50 more, and we're going to do 50 more. We're going to do one more 50 after this. And there is this box down here for theoretical. It shows you what the normal curve should look like for that population. You can see it's not perfect, but it's starting to look like a normal curve. The thing you can do with your sampling that will strengthen the relationship between the theoretical normal curve, what it should look like, and what it actually looks like, is you can increase your sample size. So now, instead of drawing 5 observations each time from this population, I'm going to draw 15 observations. And I'm going to start by just drawing 10 of them so we can see what a sample of 15 drawn 10 times looks like. There you go. Now we're going to do another 50 because the more samples, the more information we have. Now I'm going to do 50 more. And I'm going to do 50 more after this one. And you guys can start to see that what we have is a normal curve. Our means, when we draw a random sample from our population, we don't know exactly where that sample is going to fall, but we do know that it is going to be a normal curve. And we do know that with our normal curves, values outside 2 standard deviations are very unusual. And so we're going to put those pieces of information together when we try to infer from a sample to a population. I encourage you to go to this link and try different things. I am going to show you one more distribution. So let me make the theoretical go away. I'm going to give you a really weird distribution. So if our population looks like this now, you wouldn't necessarily expect to get a normal curve from that, but in fact, you're going to get something that pretty much looks like a normal curve, with most of the values clustering in the center and then other values on the outside. So the theoretical normal curve looks like that. Not bad. Just so you know, if our sample sizes could go above 15, the curve would fit even better. 15 is actually a very small sample size. Over many samples drawn, the distribution of sample means will be a normal distribution. You can add that to what you know about normal distributions, that 95% of observations are going to fall within 2 standard deviations. And you put those together and you get the wonder of inferential statistics.